Hello everybody, this is ELE 115. I have been doing a number of videos to kind of support the transition between unit circle and right angle trigonometry right up through our first AC circuit with inductance and resistance in series. Along the way, I felt that I should also provide a lecture on the kind of alternating current basics. Week 4 they talk about alternating current, and I just thought I would make sure that we covered that, and I have some slides I'll post with this lecture, and so why don't we go ahead and talk about that. First we have some facts about alternating current. We've talked about this before. If I take in this case, a 9-volt battery, and I looked at it with an oscilloscope, it would just be a flat line at 9 volts of amplitude, with nothing interesting in there. And until the battery discharged or until I overloaded or something, it would be 9 volts or thereabouts. Same thing with a regulated power supply. The regulated power supply has a reference it compares the output to, and if the output starts to fall below what you've set it at, it will boost it up, and if it goes a little bit above what you set it at, it'll back it down. So in either case, you get a pretty constant pure DC waveform, and it's not very interesting. Now if we take a square wave, as I've mentioned before, I draw square waves actually as trapezoidal waves because in reality it's impossible to switch from one voltage to another instantaneously. There's always some what we call rise time or fall time, so you'll see me kind of indicate that by drawing this sort of trapezoidal shape. But this is essentially a square wave, where I've emphasized or exaggerated the rise and fall time. But alternating current sources actually reverse current flow directionally, or reverse the current flow direction. So I think I changed that in the slides I posted. So let me see this here. You know what? Let's get rid of the AL here. We'll change the current flow direction. Here the current's flowing in one form, as one direction as the voltage climbs to plus 3 volts. The current reduces and crosses 0 and then starts flowing in the other direction as it reaches minus 3 volts, and this repeats because this is a repeating or periodic waveform. The sinusoid is the quintessential AC waveform because, as we've seen, its properties derive from circular motion and trigonometry. Now remember, the unit circle and the altitude to the vector in the unit circle is the sine of the angle formed by the vector in the x-axis, and the cosine comes from the width, the projection of that vector on the x-axis. That length is the cosine of that given angle. Now let's take a look here. I'm going to move this so you can see this fantastic drawing. And in the notes you have there is a sine wave out here. What I'm trying to show is that if you spin a coil of wire in a magnetic field, you will generate a sinusoidal waveform. And the reason it'll be sinusoidal is when we have a linear magnetic field, we have a circular conductor path, and that has a lot to do with our unit circle and concentrating on the altitude for the sine function, and on the length of the adjacent on the bottom as the cosine function. So here I'm spinning a coil of wires. If you could imagine lines of magnetic force between the north and south magnetic pole here, when the coil is like it is now, it'll be cutting the hardest across those lines of force, and we would be getting our greatest amplitude of output from the output over here. When it goes completely horizontal, it's actually moving at that moment. It's moving parallel to the lines of magnetic force, and so, it's not cutting many of them, and its output goes to zero. And then when it comes down here, it's cutting the same magnetic lines of force, but you see the top of it is cutting it from a different direction, which is why the sine wave goes negative there. And as it comes back up, it goes through zero again, and then cuts across these to give the, maybe the positive peak. I should be careful and use the left hand or the right hand rule or whatever you use to say which side will be the positive one. But it's not, that's really not as important as recognizing that a rotating wire in a linear magnetic field is exactly like how we generate the sine wave from a rotary vector looking at just its altitude. So the same idea. So that's why generators, produce sinusoidal AC. And so, now this is oversimplified, really. The magnetics and everything of a real generator are greatly refined from this. But we get an AC waveform. All right, and so let's keep going here. So why is AC advantageous, especially in power distribution? I mean, this is where, at least in the power standpoint, or the electrical power or energy distribution business, why AC is so important. AC is incredibly important in radio frequency types of systems also, but not for the same reason. It's just you need a changing signal to produce electromagnetic radiation, say from an antenna or whatever. So why is AC advantageous, especially in power distribution? Well, let's look at this thing called a transformer. So I got this soft iron square ring here. I got 3 turns of green wire on here. 1, 2, 3. Okay, and I've got 1, 2, 3, 4, 5, 6 turns of red wire. This soft iron will make the coupling, the magnetic coupling between these two inductors, extremely tight and efficient. This is a transformer. There are 2 inductors coupled together by a common soft iron core. The changes in current in the primary winding produce magnetic field changes. So, just like any inductor, if I put in energy over on this side, it'll produce a magnetic field. This soft iron is going to make that magnetic field mostly follow this path, and it's going to impact what's going on in these other wires over here. So the changes in current in the primary winding produce magnetic field changes, which are coupled through the soft iron core to the secondary winding, where they cause changes in current. So here I go current coming in, magnetism, and then the changing magnetism causes current to come out of here. So it's sort of like a motor and a generator in one unit, Okay, so this allows AC voltages to be raised and lowered as electrical energy is transported from generating stations to businesses and homes. There are 3 turns on the green primary side and 6 turns on the red secondary side. The turns ratio, secondary to primary, is 6:3 equals 2:1, or you could write it as 2:1 this way. The secondary AC voltage will be twice the primary AC voltage. The secondary AC current will be 1/2 the primary AC current. Now that's got to be true, because energy is tied to energy and power are tied to the product of voltage and current. We know that power equals volts times current. So they both can't go up and they both can't go down, because then we'd be losing energy, or we'd be getting energy for free. So it's got to be according to this ratio, and so the secondary AC current will be, like I said, 1/2 the primary AC current. And I don't know why I put this on this page. Oh, sorry. I said meters, for instance, digital multimeters measure AC volts and AC current in RMS. Well, that should be at the end of another page, so please let me take care of that in a minute. So now we've got transformers, and here's where the real key comes in. Power equals volts times current, and volts equals IR. So if I take this IR and I substitute it in for V here, I get IR times I, which is I squared R. Now wires have resistance. The power lost in resistance is heat. We've talked about that. Therefore, if we step up the voltage for the long-range transmission using a transformer, we will also wind up stepping down the current. Less current means less I squared R power loss. So we step up the voltage with a transformer. The resistance of the wires doesn't change, and so we actually wind up dropping less voltage, less percentage of voltage on the wires, and more of it on the primary of the following transformer. So by stepping up the voltage and stepping down the current, the current being stepped down, power comes from the square of the current times the resistance. So every time you step up the voltage and reduce the current, you're reducing the power by the square of the current. So it's a great effect. That's why you see these transmission lines at 125,000 volts or 375,000 volts, because they can have very low losses as the electricity travels through the wires and everything, and through the infrastructure to get to its final destination. All right, and 3. Lastly, there's this. This is where that missing sentence is going to come in handy. There's an equivalence of energy and power in voltage and current between pure DC and sinusoidal AC. So let's say we have 10 car batteries connected in series. Well, 10 times 12 volts is 120 volts. And I hook up one of those electrical resistance heaters, and it gets hot. Let's say that when it's hot, its electrical resistance is 15 ohms, which means that the total current through this thing is 8 amps DC, and 120 volts times 8 amps is 960 watts. That's kind of typical. And that heater will get warm, and put it under your desk, and you definitely get hot down there. Now with an AC waveform, a sinusoidal AC waveform, you can see that we go up to a peak, back down across zero to a lower peak, and then the whole thing repeats. But to produce the same heat, the same 960 watts as 120 volts DC and 8 amps DC, let's say we have a sine wave here that goes up to 170 volts peak. You can see this is the peak voltage, and down to minus 170 volts peak to make a 340 volt peak to peak waveform. That waveform, there's a way of characterizing it with something called the root mean square, or RMS voltage, and that voltage is 120 volts. So if I apply what comes out of the outlet to that same electrical resistance heater, I'll get a very similar power output. Those resistors will be burning heat very similarly to when they're doing it with the 10 car batteries in series, and they have 10 times 12 volts or 120 volts DC. So for this thing here, this sine wave, to make the same amount of heat as 120 volts DC, you have to have a 340 volt peak to peak waveform. Now I think this here, let's kind of just cross this out. It's a little slightly incomplete in the way it's stated. This is certainly true for a sine wave. So I'll say true for sinusoid. It would be true for a cosine wave or anything in between. And then this value down here, volts RMS equals volts peak divided by the square root of 2. Or you can multiply this by the square root of 1/2. Either way, this is the same thing. Then going backwards, the V peak equals VRMS times the square root of 2. But at any rate, this relationship right here, VRMS equals V peak divided by square root of 2, is important. And let's see what we can say here. Volts RMS, this is in AC, and amps RMS are the heat producing equivalents to VDC and ADC. So if you're producing any heat, doing any real work, you'll want to make sure that you are using the RMS values. And if I went back to this statement right here, meters, for instance, digital multimeters or even old analog meters, measure AC volts and AC amps in RMS. So we may see that in our labs. I can't remember if we do or don't. And then this particular setup right here, in your home you have these outlets. You even have ways of having 240 volts or 220 volts or whatever you want to call it. But in the classic duplex outlet, you have a larger bar, a smaller bar, and then sort of a semicircular. These are holes, right? And a semicircular hole. And this larger bar is your neutral wire. This shorter bar is your line wire. and the safety ground just travels along with your wires, and it's bounded to the neutral back at the panel, back at your electrical service panel. So between line and neutral is 120 volts AC, RMS, okay? And from line to neutral there's 170 volts peak, and between line and neutral, and because neutral and safety are connected together, you could measure this between line and safety also, 340 volts peak to peak. So you can see that the home outlet is dangerous. It accesses a lot of power, so take care with that. Please don't try to use something like this, in an experiment. All right, just respect that thing and leave it alone. All right, that's the end of this AC Basic lectures. There's one other topic in basics that we should address, and it's about real power. That is power that goes and does work for you. It drives motors, it heats resistive heaters, it does whatever it's going to do. And so there's real power, there's reactive power, and then there's apparent power. And because AC can have the voltage and the current be out of phase, means that the power company has to be able to deliver enough power to cover the cases where people are running something out of phase. And in a business, they will look at you for what's called power factor. If you're causing the power factor to be, how would I say, skewed in its phase, so that if the power factor is 1.0 or 100%, then your voltage and current are right in series. Are synchronous. They're the same phase. If you don't do this, and let's say your AC current lags your AC voltage by quite a bit, the power company will actually charge you, because they have to provide more real power in order to cover that mismatch that's created by your current demand being out of phase with your voltage demand. So just leave it there for now, but in the Cengage material, they do address power factor, they address apparent power, reactive power, and real power. So we will have a short video talking about apparent power, real power, and reactive power, and then we'll pretty much be up to week 6. We're in week 4 here. Today is February 15th, and week 4 started on Monday, I believe, anyway. So best of luck to everyone. Hope to see you Friday at lecture time, and we'll be thinking of you. All right, bye bye.